Sasha Zhiboedov. So Sasha's come from a long way away to come and talk to us and lecture to us. We are very grateful, Sasha, that you chose to join us, and we're very much looking forward to your lectures. And Sasha's series of lectures are entitled The Analytic S-Matrix Bootstrap.
Thank you very much, Robert. The eraser is...
It's stuck on the board.
Thank you very much. It's a great pleasure to be here. It's my second attempt to come, this time successful. And I will be talking about something which is a very old subject. Some of you might know this. The idea of Bootstrap and analytic S-matrix was pioneered by Stanley. One of them was Stanley Mandelstam. And he wrote this influential and important paper in 1958. Probably not many of you have read this paper, and there were a few beautiful results. Back then in the 60s, which I guess partially got forgotten, and the reason, maybe a partial reason for that, is that this matrix bootstrap people were trying to develop non-perturbative methods to solve strongly coupled theories. And they were very focused on QCD, and they didn't manage to solve QCD. And so this S-matrix bootstrap approach sort of a little bit went into the shadow and was a little bit forgotten. But lately, as you might have heard, there was a resurgence of these bootstrap methods very successful in the context of CFTs. And so the success story of CFT bootstrap, again, the idea is the same. You have a non-perturbative set of consistency conditions. But this time, you actually can solve some of the theories. So a famous example is 3D Ising model, where you can find these critical exponents. And as far as I can tell, we don't know a reason why such a success, such a great story could not happen in the context of S-matrix. And so maybe we should reconsider some of these old ideas with maybe new twists and new insights from the conformal bootstrap. And this was partially started in a recent couple of years. So there was this papers by a group by collaboration of Pedro Vieira, João Penedones, Toledo, and Baltman Reis, who started doing numerical bootstrap for the S-matrix, developing numerical methods, and they deriving some constraints. And this series of lectures or talks sort of at least partially arise from attempt to understand their methods and improve them. And so while understanding and learning this, I found it very exciting, and some of the things I thought they should be taught in the courses and should be part of textbooks, but I haven't seen them in textbooks, so I hope to tell you about this results and some new results in this context. So my plan is roughly this. Let me see how far I can get. So in a first talk, I would like to explain what. Yes, and please stop me, interrupt me, ask questions. I'm not sure I'll be able to answer all of them, but we'll try. So I will introduce you to the idea of what this matrix bootstrap is, what is the set of rules of the game. Then I would like to tell you what is the famous result. Well, so the result from the 60s known as the X theorem. I don't know if all of you know what it is. I never heard about it. So, but it's a very beautiful result. And then the second result is what is known as the Zhiboedov theorem. So, and these are theorems which you can prove using analytical methods. So you should be able to follow the arguments. And again, many of these ideas and these results are basically based on the paper by Stanley Mandelstam from 1958. In the second lecture, I would like to talk about something which is related to many developments in the conformal bootstrap recently, but this time in the context of scattering amplitudes. And so I will talk about partial waves. then I would like to introduce what's known as a Froissart-Zhiboedov representation. This is also known recently in the context of conformal bootstrap as an inversion formula, a Lorentzian inversion formula, but this time in the context of amplitudes. And lastly, I would like to talk about, well, let me call it a dragged bootstrap. It's again an idea which was not maybe formulated in these terms from the 60s, how you do analytic, you can solve crossing equation analytically in some regime. And this is, you can think of this as analog of analytic conformal bootstrap. So there will be analytics of the S matrix bootstrap. This is sort of connected to the ideas here, and so this is a result from the 60s, and maybe I'll mention something which is known as a Martin-Roy bound, which is a result from last year. Again, based on these ideas and based on the attempt to connect to this numerical result by João Penedones, Pedro Vieira, and collaborators. And lastly, the third lecture, I want to talk about some, again, bootstrap analysis but in the S metrics, but this time in the gravitational theories. It's sort of slightly disconnected, actually, but uses all the same techniques, and again, it's related to some ideas from the 60s, but applied to gravitational theories, and shocks and superconvergence. So it's related to consistency of gravitational theories when they high energy consistencies of gravitational theories. Let's see how far I will be able to get. So that's the plan. Any questions? So let me start. So the idea of the S matrix bootstrap, as you might very well know, is that we would like to consider a theory, and I will be interested in quantum field theories. So quantum field theories in Minkowski space. It will be a gap theory. So this is Minkowski space, and we prepare some states. Well, they will be massive states. So, and they say scatter. The scattering is described as this S matrix operator. So you have a set of initial states, set of final states. So you prepare large particles which are widely separated incoming particles. They are characterized by their Fock momenta. And this is the in state, and then you consider what is the transition amplitude from the in state to the out state. That's what you would like to find. And if you know this transition amplitude, you can compute the probability of the process, which is simply square. Now, for simplicity, I will be considering only theories which are gapped. The spectrum will include a single scalar stable particle of mass m. So all these particles will be scalars, and we will consider most of the time 2-to-2 scatterings. So this is a very general framework. Very many QFT fall into this category, or related, some maybe slightly different set of particles. And we would like to understand what is the space of this S matrices, what is the space of quantum field theories, and how to find this S matrices. So it's everything I will be talking is non-perturbative, does not depend on Lagrangian, etc., etc. So that's the power of this approach. Now, if you consider some normalized ingoing state. I would like to now describe the properties of this S-matrix operator. So if you consider some normalized ingoing state, because the probability is conserved, if you know that if you consider the outgoing state, which you get by applying this S-matrix operator to the ingoing state. So you start to prepare your experiment here, and you do measurements in the far future. The fact that evolution preserves probability tells you, well, the norm of the outgoing state has to be 1. Start with normalized state. And so evaluating this, we get the dagger S. And from this, we conclude that S dagger S is equal to 1. So this is known as unitarity. This is 1 property of the S matrix. Now, let's continue with that. It's a common thing in many books, and again, as you might imagine, since the subject is from the 50s, there are many books existing. So if you're interested, I can tell you which ones I like personally. It's common to write this S matrix operator as a 1 plus I t, where 1 refers to the scattering without interaction. And the way it works is, let me introduce one particle states, which are, so if you have a one particle out state with momentum 3 momentum q and particle state with momentum p, they're normalized as follows. It's again you've seen in the books, I'm sure. So the momentum is conserved. And the energy of a particle, everything is on shell, so it's m squared plus d squared. Now if we evaluate this one, if we take a 2-to-2 scattering, so we have P1, P2, P3, P4, and we evaluate this one, and so we want to understand what was the transition between this initial state with 2 particles, momentum P1 and P2, and the momentum P3 and P4, and the term without interaction, it simply gives, so if we have identical particles, we simply get, and we insert, here's the identity operator, then we get P1, P3, P2, P4, plus P1, P4, P2, P3, where these are the norms, and this corresponds to simply no interaction. Particles pass through each other. The most interesting part is coming from this T operator. So it's common again to, if we consider states say with momentum P3, P4, T, P1, P2. We write it as 2 pi the d momentum conserving delta function. So since we assume that the quantum field theory is relativistic invariant, so the energy momentum is conserved. And then there will be a function which is a main player of 2 variables. As everything in this talk, it's named under Mandelstam, so these are called Mandelstam invariants. And in a center of mass reference frame, takes the following form, which you again probably seen many times. Everything which I will be talking about today is very importantly happening in dimensions, space-time dimensions larger than 2, because usual 2 dimensions, it's a very special story, and in contrast to high dimensions, in 2 dimensions, we know examples of interacting and non-trivial S matrices. But one of the interesting thing about, well, one of the peculiar thing about high dimensions is that there is no, we don't have a single example of interacting theory, interacting S matrix which is fully consistent. So we believe, of course, they all exist, but there is no example that we know. So this K is, if you think of as the usual, if you think of scattering and center of momentum frame, so 2 particles come with opposite momentum, K minus K, and then they scatter an angle theta as momentum is preserved. So that's kinematics. And let me draw. So we will be interested in trying to understand the properties of this object. And it's useful to think about, so we have ST and U, which add up to 4m squared. And it's useful to think about the problem in what's known as a scattering diagram, or it's called a Mandelstam plane. So let me draw it, and then I will add features to this plane as we proceed. So Mandelstam plane is describes different regions in this S and T parameters. So let me draw it. Mandelstam plane. The way you draw it is like this. So this is T, this is S, and U will go in, because U is 4m squared minus S minus T, it lives on the diagonal. So there is a 0, there is 4m squared, there is 4m squared here, and there are a few regions. So here, when we have a few regions, which these are called physical regions. So in particular, for example, you see here, S is positive and T is negative, and between minus 4m squared minus S. And this describes the scattering of particle 1, 2, 2, 3, 4. Similarly, here you describe particles 1, 3, 2, 4. Finally, here there is a say U equal to 4m squared. There is a region which describes particle scattering 1, 4, 2, 3. So what I mean by that is, recall again, I wrote this S to be 4m squared plus k squared. So if you consider physical scattering with momentum k, you see that S is larger than 4m squared. So therefore, physical things happen only, say, for S larger than 4m squared, and T, for the purpose, is 2k squared sine minus 1. So you see that for any physical angle, T will be negative. So we are below here, and then it takes its maximal value along this line, which corresponds to the theta being applied. Now, so you might naively think, okay, we started with this function of 2 variables, S and T, which only we take physical and real, so they're real variables living in some region. But the deep fact about S matrices, I guess, and the fact that they're coming from local quantum field theory is that actually there is a very rich analytic structure. So we should think of this function T of S and T as living really in C2. So each of these variables is complex, and the scattering amplitude is a physical scattering amplitude. Is a boundary value. Of a single analytic function. So this again was established, and I guess in the QFT courses we learned this as the I epsilon prescription. So the physical scattering is described as a limit when you land. It has to be positive, but in upper half plane, and then we land on the real axis.
So, why statement local field theory? Why?
Local and local and causal. I mean that this results, as far as I understand, we start with a QFT with local fields and commutators which are zero outside the light cone, and then you do LSZ reduction, and you see that there is a
string scattering amplitude.
I think it's believed that they also satisfy these properties,
Yeah,
but
let's give up local now.
I don't know how non-perturbative rigorously what.
Maybe it's not the property of local at all.
Yes. Here, I think important. I guess one thing is that here these results are rigorous and true.
So you can show.
Yes, but I totally agree that local.
There might be a large class.
There might be a larger class, absolutely. I totally agree. Yeah. So. So there is this analytic structure. So there is this function of S and T, which are now complex variables. And you can ask, okay, what is the analytic structure of this function, which was like there are hundreds of papers dedicated to establishing analytic properties of this function. And there are many results which are proven or believed. For example, there is a famous proposal by Mandelstam known as Mandelstam representation, which I think which was never proven, and it's more than we can derive from local field theory. But as far as I know, it might be still true that many local quantum field theories satisfy that. But
sorry, can I have a quick question?
Yeah.
So why is this I epsilon limit involve S but not T?
Well, let me go into this. I will now explain this. Yeah. It's basically it will be because here we will be, so the T will have a branch cut, and then you have to specify from which direction you approach the branch cut. For T, it's just we in a region where nothing happens. For physical scattering. So okay, recall that we had this relation for unitarity as dagger equal to 1. And if you plug S equal 1 plus IT, you get that's what's known as an optical theorem. So you get this relation. And in particular, if you sandwich this equation between the two particle states, you see this picture that if you have a scattering 2 to 2. On the left-hand side, you take an imaginary part of the amplitude. And on the right-hand side, if you sandwich it between some state, you can insert a complete set of states here. This is given by sum of all states. Here again. So this statement is known as the optical theorem, and here is sum over all intermediate states. So now you see that there is, from here you immediately derive the notion of a normal threshold. So normal thresholds are simply the S for which you have enough energy to create, let's say, this number of states. For example, the minimum, if you have n particles, here is the minimal energy that you need to create n particles, n squared. So if you have n particle states here, you need S larger or equals than n squared. So that's why, for example, if you have a 2-particle state, S has to be larger than 4n squared. 3-particle states, it will be 9, 16, etc. So for simplicity, I will assume that, it's a simply technical assumption that particles carry some kind of parity or some kind of symmetry, which makes it, which prohibits the amplitude of this type where you have, say, even say 2 particles here, and odd number of particles here. So this I will set to 0 and assume that there is some symmetry, so this is 0. And it's not fundamental, it simplifies some of the discussions. Now, you see that we have, if we draw in, say, the complex S-plane, we see that that when S is larger than 4n squared, there is some singularity, so the amplitude develops a branch cut, such that discontinuity along this branch cut is given by probability, and then there are some thresholds. When here we have produced 2 particles, then we'll have start production of 4 particles, etc. And similarly, you can go to this other channel, 1, 4 to 3. So when U is larger than 4n squared, when U equal to 4n squared, recall that S plus T plus U is equal to 4n squared. So when U is equal to 4n squared, S is equal to minus T. So similarly, there is a cut here, which starts at minus T and go all the way to minus infinity. So now there is a belief, or assumption, if you wish, which I also will follow. It's what was rigorously proven as part of it, but I will assume what is known as a maximal analyticity, and I will assume it just for scattering of identical particles, because there are some other phenomena like anomalous threshold, which might happen for non-identical particles, but so maximal analyticity. And maximal analyticity tells you that the minimal singularities that are required by unitarity are all singularities that are present. So what do I mean by that? So we see from these equations by unitarity there should be some kind of branch cut at 4n squared and 16n squared. It has to be there, because otherwise you will not be able to satisfy this equation. Similarly, in the cross channel, when you go to this region, and again, note that there is a beautiful fact again. We started with a function defined only here, and only here, but now we have a single function which interpolates everywhere. So you can go wherever you like. Similarly, we have the set of normal thresholds here, and in principle you can contemplate the possibility that there are some other singularities. So maximal analyticity assumes there are none. So the only singularities of this function. In each variable, we have simply the cut for normal thresholds, and it's crossing symmetric, and the same in a t-plane. So I will assume that. And similarly, you can use some arguments to show that amplitude satisfy what is known as Hermitian analyticity. You might have seen that which states the following thing. So I told you that the physical amplitude is described by approaching the cut from above. This you can derive, say, using LSZ prescription, etc. So here in this equation, you see that you have a T dagger, which describes the complex conjugate amplitude. So what Hermitian analyticity tells you that the process described by the Hermitian conjugate process is described again by the same function, but when you approach it from below. So therefore, we write here this, we started with T dagger and then wrote the imaginary part, because we can relate this T dagger to the function here. And it's also related to the fact that actually, so the function is analytic, and you can show that it's real here for real T, and then this is just the way you analyze for the continued function.
So for ordinary field theory, this follows from Hermiticity now?
I think so, yeah.
But maximum analyticity, again, that would be automatic in ordinary field theory?
It was never proven in perturbation theory. It's
We assume regular propagators. And not the only one. Yeah. Okay.
Yeah, I guess.
Some weak assumptions, strong assumptions. Yeah. But in a non-field theory, that is very difficult to contemplate.
I would.
Here the table of reverses. This is easy in field theory, but not for some string theory or something. You wouldn't do this for string theory. So
Right.
okay.
Yeah, I don't know what's actually I would not be surprised that if its analyticity properties are the same. For example, there is a thing which is more specific about QFTs, which is another property. Let me just name it so that we have all of them, which was again proven in the 60s for some T's, which is a polynomial boundedness. And this is something which I suspect is different than, say, gravitational theories or string theory. So it was proven by F and 64, and then Epstein, Glaser, and Martin. It's 69. So remember, I started in the beginning by quoting a paper by Martin and Roy from last year. It's the same Martin. So he works on the subject for a long time already. And so what the guys proved that if you have, say, t less than 4 squared, that in QFT, just from Whiteman axioms or some other ways that you like to, maybe hard axioms, the way you like to prove QFT, you just need 2 subtractions at most. Dispersion relations, or I haven't explained what dispersion relation is, but it tells you that if you go to complex plane and you take an absolute value of S to be large, that the amplitude is bounded by some number times S squared. So to reiterate, we have so far a function of 2 very complex variables with certain analytic properties, which satisfy, so we have these equations, which is unitarity, and note that here on the left-hand side we have just 2 to 2 scattering, but on the right-hand side other scattering amplitudes appear. And so another condition that we want to impose to finish with this thing is what is known as crossing. So crossing is it's a very simple statement here. So if you consider scattering of identical particles, the particles are indistinguishable. So the amplitude t is equal to t and s, u and t, etc. Basically, it's a function which is symmetric and all permutation of Mandelstam variables, and this is a statement that that the particles are identical. Okay, so now let me formulate the idea of a symmetric bootstrap for the question, and it's very simple. You want to understand what is a space of S matrices and what is the properties which are consistent with unitarity, analyticity, and crossing. And here I can include also polynomial boundedness. So that's a goal. If you can say something non-trivial about the space of the solutions, that's already very interesting. About this set of functions, as I told you, we don't know a single one which is sort of physical and not on the rising theory.
Yeah, good question. So on the left-hand side, so T is so as you mentioned, the left-hand side, the T here involves 2 in, 2 out.
Yeah.
But on the right-hand side, 2 to many,
Yeah.
potentially.
Potentially.
But these conditions compare this polynomial boundedness, that only refers to the 2 to 2 case.
I will refer to 2 to 2 case, yeah.
But, and that's enough? Is it expected that one doesn't have further conditions?
I think it's expected they're all polynomially bounded. Yeah, all of them. So if you take n-point amplitude, and we take some Mandelstam invariant, it should be polynomially bounded, but the number of subtractions, here it's proven that it's 2, I don't know what's known about subtractions for high point amplitudes. Okay, that's the basic idea, and now I will start trying to prove some results about this object. So let me start by formulating what's known as Axe theorem. It's a very beautiful plane. And it was proven by Stanley Axe in 1965. It says that scattering implies production in D larger than 3. So that's it. So what does it mean is that imagine you assume that you have some quantum field theory or some S matrix where you have 2 to 2 scattering. Now you can ask yourself, could it be that all the amplitudes with higher point functions where you have productions are 0? So that this amplitude is non-zero, and these amplitudes are 0. And we know that in 2 dimensions, it's totally possible. It happens all the time, and all the exact matrices we know, the integrable ones, they have this property. And so you might have asked yourself, can I do something like this in high dimensions? And this theorem tells you no, it's impossible. So in high dimensions, if you have scattering, you will get production. And an interesting twist on this is that if you look at the results of a numerical bootstrap from last year by this set of authors, sorry, I forgot to mention Miguel Paulus also, so let me just, Paulus, Benedones, Toledo, Van Rees, and Vieira. So that's a paper from last year. They were trying to, as you know, in a conformal bootstrap, one of the approaches that you try to maximize things. You try to make interaction maximally strong, some gap in a spectrum of operator is large, if possible, and then you find some interesting bounds. So what these guys try to do is they try to maximize the strength of the interaction. So there is a way to, you look at the amplitude and then, so this triangle is known as a Mandelstam triangle. So you look at the amplitude here and you try to maximize it. And they do it numerically, and so they found something which looks like scattering without production, which is puzzling, because we know, according to the theory, the scattering does not imply that the scattering without production is not possible, and it's, I think until today it's an open problem what happens with the numerics. Either the production is small that they don't see it, or something goes wrong, etc., etc., etc. So this is something, if you wish, motivated. We're looking at this not only because of historical curiosity and beauty, but also it has a direct connection with the recent developments here. So how do you prove such a thing? Especially, you naively would think, okay, well, they see it numerically, why not? I mean, what's wrong with that? And the proof of this theorem is very beautiful.
Sorry, so you said in numerical bootstrap, they see this happening?
They see numerically exactly this type of amplitude. This is non-zero, this is 0. So, and then you might wonder, the precision is small enough, what is the bound? So imagine that these are non-zero, but they're 10 to minus 1000. Is it consistent? And so it opens up all this can of worms. What is a, and the Roy Martin bound is exactly as a they try to bound the minimal inelasticity, etc. So the question is how small inelasticity could be.
Sorry, for which theory do they do
This?
Yeah. For what theory?
Just any scattering implies production, any theory.
So what they do numerically is generic? Or?
Yeah. They assume exactly what. So everything I said, they assume. So they assume some QFT with a stable particle. There is a S matrix. It's unitary. It's analytic, and they bootstrap an S matrix.
Okay, so there's no extra electrical symmetry.
No. Yeah, there is nothing.
What dimension are they in?
4. Yeah. And well, the original proof by Axe is also 4-dimensional, but people were obsessed with QCD, so but it's also generic.
So this numerical work is not for conformal theories.
No. It's a for massive S matrix. Yes. Yeah, it's a. I can tell what they're doing, but
They knew about the theorem, no?
I think yes, because they quoted, but I don't know if they how much they.
It was kind of, I didn't know that was Axe's theorem, but the theorem was known.
Yeah.
Kind of verbally, that's all.
Right. So I think they were aware, and they're aware of this situation, and well, it's to be seen what's happening. So let me, and you know, in the conformal bootstrap, some things, well, we have crossing, we have analyticity, we have some sort of unitarity, but the way you prove this theorem is you're using essentially that there is a gap. And that's one aspect which I find beautiful about that is that, and how does it come about that the gap is crucial to prove this theorem? So the idea is the following. Note that, as we discussed, if we look at the 2-to-2 scattering amplitude, so we can produce these particles potentially, but there are normal thresholds. So consider the energy which is larger than 4m squared and less than 16m squared. In this region, its energy is enough to produce 2 particles, but it's not enough to produce 4 particles. Right? For the 4 particles, you need 16m squared. So therefore, in this equation, you have imaginary part of this amplitude is given by the square of the amplitude itself. And there is nothing else happening, so it's a closed equation. This equation, which is not possible in CFT because if the CFTs are not gapped, so m is 0, and so all the normal thresholds that pile up on top of each other. So you do not have this equation, and this equation is known as elastic unitarity. And actually, elastic unitarity is something that these guys did not impose. It's just for numerical reasons, it's hard to impose elastic unitarity because it's a nonlinear equation. So is it clear? Okay, so now that here we are in this region, so we stay better in this region for this equation to hold. Let me introduce, so I introduce this notation, TS. I think it's against standard since the old times. So we consider the scattering amplitude above the cut minus below the cut. Then the unitarity equation, it says that twice imaginary part of this amplitude, or discontinuity, the better way to call it discontinuity, because very soon it will stop being imaginary part. And on the right-hand side, we have this complete set of states. So this is a general form of the optical theorem. And when the only states which contribute are two particle states, we have the following equation. Twice imaginary part, and we sum over all states that appear here in the intermediate states. And here we have a momentum preserving delta function. And here we have, so the energy is preserved, so we have T star of S and T prime, and T, S, T double prime. Where T prime is minus E1 minus Q3 square, T double prime is minus 3. So again, the idea is simply we start with particles, say 1, 2, 3, 4, 1, 2. This is a two particle state labeled by Q3 and Q4. And so they can scatter in different angles, so we have to sum over all states by usual resolution of identity in quantum mechanics, and sum over all states is the same as summing over all momenta of this particle. And then for each of the blocks, we insert a scattering amplitude. That's a thing, and again, if we work in a center of mass frame, so you have two particles coming, so then these momenta, again, are opposite to each other. Total momentum is 0. And by momentum conservation, their absolute value is also equal to the ingoing momentum. So really, the only degree of freedom here is the angle, scattering angle, which is expected. So let's rewrite slightly this equation. Namely, we can integrate out this delta function. And if we integrate delta function out and simplify this equation, we get the following equation. How much time do I have?
You still have about 20 minutes.
20 minutes, perfect. So if you simplify this equation, it takes the following form. Ts is a discontinuity along the S channel. You get this momentum. Again, particles colliding with momentum k and minus k. Particles 1 and 2. You get 2 pi t minus 2. You get 16 omega k. This is again the energy. And here you have an integral over all angles of an intermediate particle, where we can rewrite now the scattering amplitudes as a function of an angle. So recall that the t variable was related to this minus over 2k squared or minus k squared k squared cosine theta minus 1. So here we k squared. So here this, let me introduce variables now. I will introduce instead of cosine this variable z. So z, and this is what the amplitude depends on the left. Z is the angle between the scattering angle between, say, P1 and P3. It's a cosine theta. And similarly, z prime is the angle between P1 and this intermediate particle over which we integrate. And z double prime is the angle between the outgoing particle and this intermediate particle. So what Mandelstam did is he realized that how to take this equation and analytically continue it in T. You know, we started with S between 4m squared and 16m squared, and T being negative for physical process. We're describing physical process. And now the idea is to analytically continue this equation. How to do that? So the way it works is the following. We write down a simple representation for these amplitudes. So, for example, we have this T as z double prime, and we write it as a Cauchy integral 1 over 2p by I t eta double prime t s double prime eta double prime minus c double prime. So recall that z is an angle here, so it takes value between -1 and 1 for physical scattering. So you can take any z between -1 and 1 and write this contour integral. So this is a contour integral. So for any z, this integral just picks you a residue, which is amplitude itself. Therefore, if you plug this, note that if you plug this representation, now all the dependence on z prime and z double prime, which is this angle over which we're integrating, is factored out in these prefactors. So we can completely do this integral. And that's what we do next. What we get is now the following expression. That the discontinuity is equal. I will, let me set maybe, okay, well, let me not set. I will have all the factors. And we have these contour integrals. And here we have the kernel, which emerges from this, doing the integral over this intermediate angles, and the scattering amplitudes as a function of this variable. So this is, and now recall that by known properties, analytic properties of the amplitude, we know that the amplitude is analytic in T. And if you maybe you don't remember again, so let me write T is equal to -2k squared. And here there is this variable z, which is equal to cosine theta -1. So the analytic properties in T are translated into analytic properties in Z. And so the idea is now we can start deforming, we can now, if we try to analytically continue this in Z, we will find that actually it's analytic in some larger domain. So this formula is very nice for analytic continuation in Z. And in principle, you can compute this kernel in all dimensions. But let me write the answer in 4 dimensions. So in 4 dimensions, the kernel takes a form plus to infinity g theta over minus z. F theta plus minus given by this formula. Prime and double prime plus minus. Now it might look a little bit abstract, but the formula has several crucial features. So first, the integral starts from n plus, and the dependence on z is just through this prefactor, 1 over f eta minus z. What is this n plus and n minus? Well, you can show that from this maximal analyticity. Remember I told you that we have two cuts, so we have two cuts with normal thresholds in t. You can ask, what does it imply about analyticity in this angle variables? Z. And this is what is known as Lemon ellipse. That it implies you can show that the amplitude is analytic in some ellipse. In this, partial wave expansion will converge in an ellipse, but it's analytic in some region in these variables which have some cuts. Now what happens is that, let's say you start increasing z. You would like to increase this z variable, which is related to t, and you want to go to some unphysical region, and you ask, well, what happens is that you have a singularity when you have a potentially singularity here. So what you would like to do is you would like to deform the contour so that. Okay, let me try to explain it again. So eta plus and minus depend on eta prime and eta double prime. We want to analytically continue the left-hand side in z, and ask when does it develop, say, singularity. What happens is that if you have a complex integral to develop a singularity, the two things normally happens is either you contour pinched between singularities, or you have some kind of endpoint singularity. So what happens is then you try to deform the contour, and you ask when there is a pinch. So when you try to, we started with these contours, and you try to deform them, you know that there are cuts here. These cuts are starting simply when t is equal to 4n squared. And these cuts are located at the position is known as a1 of s and minus a1 of s. And a1 of s is what happens if you take, so this is this momentum k, you can rewrite it as a function of s. So this position, as we discussed, starts when t is equal to 4n squared. So you can rewrite, so the cos theta to z in a general reference frame is equal to 1 plus 2t over s minus 4n squared. When you plug t equal to 4n squared, you get this a1 of s, which is 1 plus 8n squared, s minus 4n squared. Now, what does this n plus, n eta a plus and eta a minus? So what happens is that if you try to look at the contour, say in eta plus, if you have an integration contour in eta prime and eta double prime of an ellipse of some size, so then let's say it's ellipse of some size x. Then what happens is that you can check that the contour that these two variables describe in the variable eta prime, eta plus, is an ellipse of a larger size. And the size in this ellipse is known as a large Lemon ellipse. And so in eta plus, you get an ellipse of size 2a1 squared s. This you can check by simply taking n, because this variable, this formula with a plus is nothing but the trigonometric identity for angle of twice. So if you plug eta and eta prime in a1 and a1, you will get 2a1 squared minus 1. So the punchline is that as you try to analytically continue in z, you have the singularity. To avoid the singularity, you analytically extend the contour in eta, but at some point you start hitting the cut. and then you cannot deform the contour anymore. And so when you z approaches the cut, you can approach from either above or from below. And so there the integral develops a discontinuity. And this time noted that we already took discontinuity in S, and now we analytically continue in T. So this is what is known as a double discontinuity. So it's imaginary part of an imaginary part. This was introduced by Mandelstam. And by doing this and deformation of more carefully and taking this discontinuity, you get simply that the double discontinuity of the amplitude, which is now we continue in T above and below the cut, is given so let me now denote this T in S and Z. It's given by discontinuity of this kernel. And recall that this kernel depends on eta through only 1 over eta minus z. So the discontinuity of this guy is simply a delta function. And the integral was from eta plus to infinity. So if you integrate the delta function from eta plus to infinity, you get some result with times a theta function z minus eta plus. So the kernel of elastic unitarity is such that this guy has double discontinuity only for z's larger than eta plus, where eta plus was related to the position of this cut, and here it will be related, so it's given by 2a1 squared. So it's twice the plot. It's an ellipse of a larger size. And the formula that you get for the double disk is this. It's integral over the cuts. Then here you have discontinuity of the amplitude. So when you take this amplitude, integrate along the contour, and you deform it, you take discontinuity of this amplitude. So you have a product of two discontinuities, but now discontinuity is in T, because this is a z-plane. So we have this beautiful formula times the discontinuity in Z. Okay. Where discontinuity of Z of this kernel is 4 pi squared, as I told you, theta function of Z minus theta plus. And here you have Z minus theta minus Z minus theta plus. So that's a result. And now let's see what this result implies. Note that it's all very general here. We didn't assume much. So first of all, you see that the double discontinuity is non-zero only when Z is larger than eta plus, where eta plus is given by this. So what is this equation? Z is related to T. So what is the equation Z for theta plus? Well, Z is related to cosine of theta, and it's equal 1 plus 2t over s minus 4n squared. And eta plus is given by this formula, which I wrote before, what A1 is. So Z being larger than eta plus transforms into the funny condition T larger than 16m squared plus 64m to the fourth s minus 4m squared. So again, to recap what we did. We started with elastic unitarity. We analytically continued in t variable. We started with elastic unitarity in S. We analytically continued in t, and we discovered that amplitude develops double discontinuity. And then we found that the double discontinuity only develops in this region. So this curve, when t is equal to this, is known as Landau curve. It's kinematical, and that this region here has support somewhere here. So you see that when, first of all, when S is larger than 4m squared, then t is larger than 16m squared. And when S goes to 4m squared, this goes to infinity. So the way it looks like is like this. And here there is a 16m squared. So there is this support. And this function is known as double spectral density. So now we have these regions here. If we draw a little bit more carefully, so there are these regions. You can also find it in the books. That there is a double discontinuity of the amplitude really in these funny regions, and this is a fact. So what Mandelstam then did, he derived that, and then he assumed that this is a sort of wrote a natural ansatz which incorporate this in full generality, and this is known as a Mandelstam representation. Now, Landau singularity, so I told you this is called Landau curve. Landau singularities, and this we discovered in perturbation theory. These are the questions when Feynman diagram develop singularities, and this is completely kinematical. It does not depend on interactions much. Like here, we did not assume much about interaction. We found this curve. And the diagram, natural diagrams that you can draw for this process is the following. So we started with considering this cut. So we have 2 to 2 amplitude. And then we try to take a double discontinuity, and roughly what we found is that we have some process of this type, where here what I mean by this is simply that here we started with Ts equal T star times T. So the left hand side is T star and then T. And then we were trying to take a double discontinuity. So we take this amplitude and we take discontinuity and the other channel. And the first channel that we discovered is this. It's again two particle. And you see now something very nice happens. We start with 2 to 2. And now there are 4 particles that are appearing here. It's a double disk, and you might already see in a production, so hints of production, but really to see the production, and I think this is a crucial observation of X, is the following, is that he noted that, let me draw this region of support of a spectral density. So he basically noted that this condition for the support of a spectral density is not crossing symmetric. So the double spectral density, because everything is crossing symmetric in S and T, and here you can argue that from analyticity, basically that this double discontinuity should not depend on the order you take the disk. And so then you want to impose this crossing symmetry of a double discontinuity. So that's a crucial idea. So let's try to impose a crossing symmetry of double discontinuity. So we want to have this double spectrum density, S and T, which is T, S T to be equal to, and this is a statement of crossing. Now let's draw this region. Let's draw this region. So again, it's T and S. So we have here 4n squared, 16n squared. And here also we have t in 4n squared, 16n squared. So what we've shown here is that for t less, the spectral density is 0 for t less than or equals less than 16m squared plus 64 m to the 4 s minus 4 squared. So what is this region? When s goes to 4, it goes to infinity. So we found this. So the spectral density is 0 below this curve. It has to be 0. And now, but we can apply, so elastic unitarity was formulated in this condition. So we got it in this strip. It should be 0 below this curve. Now, what is the crossing symmetry image of this curve? Well, the crossing symmetry, we just flip s and t. So we get s is less than 16m squared plus 64 m to the 4 is t minus 4m squared. And so there, the spectral density should be 0 there as well. It's just a crossing symmetric transform. So let's draw this curve. Now, when t goes to 4m squared, s goes to infinity, and s is always larger than. So we get this curve. Now here comes the crucial fact about theories with no production. So in a generic theory, which has production, elastic unitarity applies only in this strip. So we have that in this strip, the spectral density is 0 here, and in this strip, spectral density is 0 here. Now imagine that there is no production. The part is that if the theory does not have a production, that's the assumption of X. If the theory does not have a production, the assumption, this elastic unitarity, it applies not only between 4 and 16, but it applies also for larger values, right? Because new channels do not open. If you have a no production, then in unitarity conditions, before, if you have a 4-particle production, when s equal to 16m squared, you start producing 4. But if you assume there is no production, the equations that I wrote, which is elastic unitarity, continue to hold. Therefore, in a theory with no production, you can erase these borders. So the amplitude that you can apply this result for any s larger or t larger than 4m squared. And now you see what happens. That from the direct channel that I did for you, we concluded that the double spectral density is 0 here, but here we already expect to get some spectral density given by this equation. On the other hand, if we apply cosine, we get that the spectral density should be 0 here, because it should be 0 below this curve. So therefore, we get, from non-production, we get the statement that if we go to this region, well, the spectral density should be 0. So we get 0 in this region. Now the thing is that because the discontinuity here contains a theta function, this integral between a1 and infinity is actually capped off, so it doesn't go to infinite energies, and you can use the basic unitarity equation. Remember that we have this always equations that imaginary part of t is equal to t squared, roughly. Well, it's up to these integrals. And so here now, if you apply this equation here, because it's the discontinuity in the dual channel, you get that this discontinuity in T is equal to something square. And you can check that in this equation, so it's positive definite, and you can check that when you stay in this region and you do this integral, everything is positive definite. Therefore, we conclude that from crossing, so we start with elastic unitarity, we analytically continue, we assume no production, we use crossing, and we're concluding now that the discontinuity of the amplitude in this region is 0. But it's positive definite, so the amplitude itself is 0. So we prove the X theorem that no production implies no scattering. So it's a very beautiful argument. It uses everything that we didn't have much, but it uses in a very smart way everything that we basically have. How much time do I have?
You can stop any time now.
Okay. So let me just mention one more result, which is like a one line. If you can digest what happened here, then there is one line to prove what's known as a Zhiboedov theorem. And Zhiboedov theorem is also very simple to formulate. So Zhiboedov theorem states that if you wish, you can formulate it like this. Relativistic object cannot have fixed size. What do I mean by that? So the size, if you consider 2-to-2 scattering, you can imagine a target and a projectile, and so you measure cross-section. You define a cross-section as the size of the object. You can ask, could it be that it cannot have fixed what's the state? Size. Size has large energies. So what does it mean is that imagine that your cross-section is asymptotically constant with large energies. What does it mean? It means that your amplitude by optical theorem, the imaginary part of the amplitude is related to cross-section by simple rescaling by S. So if the object has a constant size, it means that the amplitude asymptotically has a form which is linear in S times some function of T. So then a cross-section, you set T to 0, you divide by S by optical theorem, total cross-section is just constant. It's a function of S. Now, if you assume that, and you plug this in this equation, so you take this formula and you plug this in this equation, and you try to take S to be very large. And what you find is that if you look just at this kernel and this integral, that as you take S to be large, then you find that the scaling with respect to S in the left-hand side and the right-hand side is different. So you get something like S, the left-hand side, and then the right-hand side, you get S log S. So this cannot be true, therefore this cannot be true. And then Froissart generalized this to the statement that if you try to write here something like S to the P log Q to the log S to the Q f of t, then such asymptotic is inconsistent for any P and Q larger or equal than -1. Another way to state Zhiboedov theorem is for those who heard about Reggie theory, to state that there couldn't be a fixed J singularity at large energies. So this corresponds to the fact that these guys do not depend on T. Is fixed singularities in J plane. And this was important questions, I guess, and they're still important because we would like to understand high energy behavior of, say, protons at LHC, and you have to understand this kind of asymptotics. And I guess there is a long story that people first believe that the cross section will be constant or decreasing, and then slowly this views developed. And so in this theorem, he proved that it cannot be constant. And again, the proof was really one line. You take this formula, plug it here, and estimate this integral with the known kernel, and you find an inconsistency. So it's a very neat result. So I guess I'll stop here. And the idea of next lecture would be, so here we show that there must be an elasticity, and next we try to derive some quantitative prediction about this inelasticity using some other methods. Thank you.
Any quick questions for tea if anyone wants to ask? Or we can handle them over tea. So listen guys, it's now 5 to 11. Let's get back at 11:15.